Hi everyone, and welcome to this video. In this video, I want to go over Euclidean spaces and especially vectors and vector spaces. We're going to talk about vectors, what vectors are, and then get into vector spaces. But before starting, let's talk about linear algebra. What's linear algebra? Linear algebra is the study of sets called vector spaces. So that's a set. And just to refresh your memories, put a little example of a set. For example, this is when you have the set notation. So you use those curly brackets. And this is just set of whole numbers, 1, 2, 3, or set of not whole numbers, but natural numbers or counting numbers, 1, 2, 3, 4, 5, 6. So that's a set. When we talk about a set of vectors, so these are just vectors which I'm going to tell you what they are. Now, in linear algebra, what we do, we generalize. It's just generalization of numbers, their structure, and we have functions with special properties that they're called linear transformations that map one vector space to another. Now, in this lecture, please pay attention to the vocabulary or some words that I have underlined because we're going to see this throughout our next lectures. And that's one important part of this lecture. So first, the vector space is set of vectors. So we write the set notation and we place vectors in that set. And we can check to see if that can be a vector space or not. That's coming. Then don't forget this word linear transformation because I'm going to have one or two separate lectures just on linear transformations. And that's what you take a vector space and uh, use linear transformation, and that's going to map that vector to another space. So now let's just talk about vectors. So a vector is an array that has a direction and a norm. So what can you do with vectors? Let's go over the operations first. You can do vector addition. So if you have two vectors here, for example, I have a vector u and a vector v. If I add these two vectors, then I get the diagonal of that parallelogram. So that's why we call it the parallelogram principle. So if I draw the parallelogram, that's u plus v. I will go over the details of that, but this is, we get that by vector addition. You can also have vector subtraction if you subtract two vectors, and I'll show you the details. So if this is vector u and this is vector v, if you subtract them, you get this vector here, that's u minus v. Usually we get we call this the triangle law for vector addition. Why do we say vector addition? Because vector subtraction is just u minus v is u plus addition, and the opposite of it. That's what happens. The third operation is scalar multiplication. You can take a vector and multiply that by any number you want. Here I took u and I multiplied it by 2. So what we get is twice u, but same direction. If I multiply this by negative u, then so negative 2u is going to have an opposite direction. So vector addition and scalar multiplication. Remember these words because we're going to use this a lot. I put a note here. Two vectors are parallel if one is a scalar multiple of the other one. These two are parallel vectors because one is the scalar multiple vectors. This is, if I call this vector v, so v is 2 times u, and they are going to have the same direction. So that's scalar multiple, it's just multiplying the second vector, taking the vector and multiplying by a number. Now the from operations 1, 2, and 3. So 1, 2 was just addition and subtraction, and 3 was scalar multiplication. We will construct linear combinations of vectors. Again, remember this word, linear combination, and I will explain that to you in the next videos. But for this video, again, please remember those words and form a span of the set of vectors. Remember the word span. I'm emphasizing on this word because you're going to see that a lot in the next videos. Now, spans are example of subspaces. So we can have a vector space and we can have subspaces. These are also vector spaces, the subspaces. And again, I underline this word, so I want you to remember that word. The subspaces can be described as the span of finite set of vectors called bases. It means you can write if you have a basis, and remember this again, the details you're going to see in the next videos. So you can form a vector, a subspace in that vector space. Now, before getting to all vector spaces, subspaces, span, and bases, let's go over the properties of vectors or properties of vector arithmetic. Now, if you have, let's say we have three vectors, u, v, and w. These are vectors. And r and s, it could be d and s, r and s, alpha, beta. These are scalars, just numbers. So the properties that are closed under, when you see this is vector addition. That's what I decided to do. When you see plus with a circle, that means vector addition. That means if u and v are in Rn, then u plus v is also in Rn. Then you have closure under, when you see this sign, that means scalar multiplication. In the next video, I do all the details for this. This is just R times u. That means if a vector set in, it's in Rn, then R times u is also going to be in Rn. Be careful, we're gonna get there in the next, just be patient, and I'll explain those in the next videos very clearly by doing examples. You can have the commutative property. A vector u plus vector v is the same as v plus the vector v plus vector u. Then you have the associative property. U plus v parentheses plus w is u plus v plus w inside the parentheses. Then you have the additive identity. So zero vector, this is the way you write this. That zero vector plus vector v is v plus zero vector, and that's going to just give you the vector v. You can have the additive inverse. A vector plus its opposite is going to give you the zero vector, or vice versa. Then you can have the distributive property. These are scalars. R plus s times v is rv plus sv. So then you can have the distributive. We can distribute the vector, or for number 8, you can distribute the scalar. R times u plus v is ru plus rv. Associative property of SM. SM stands for scalar multiplication. So R times S, these are two scalars inside the parentheses times V equals to R times SV, or you can say S times RV. It's the same thing. And of course, the multiplicative identity or the scalar identity, 1 times any vector is going to give you that vector. So these are the properties of vector arithmetic. And again, in the next video, I'll show you the details. Now let's just talk about vectors in Rn. One thing I want you to be aware of, the way you can write a vector, you can write u with just an arrow on the top, and that's what I use in my lectures. Or in some books, it's written as bold U, or you can just have U with just one, the arrow is just on the top, so just like that. So these are three ways you can write a vector. So, and I am going to be using that in my lectures. You can use, when you write U, you can put U1, U2, U3 inside the parentheses. These are the components of that vector. Do not put arrows on top. So these are just components, these are just numbers, I'll talk about them. Or you can write U and you use these brackets, and these are called angle brackets, and put the components. And again, that's what I'm going to use in my lectures. So for vector, I'll use that. And for the components, I put the components inside angle brackets. You can show like the matrix notation. So this is put the components U1, U2. So that's like a column matrix. And that's a row matrix. And again, this has an arrow on the top. That has an arrow, but not the components. The components, when you don't put an arrow, these are just numbers. These are the components of that vector. Be patient and we'll go over that. Actually, it's right here. Finding the components of a vector. So if you're given an ordered, the ordered pair, so this is just a point, x1, p and q, x2, y2. So if you want to find the components of the vector that joins P to Q, that vector, you can call that U. So you write U and you can just do x2 minus x1, y2 minus y1. Let's do an example, see what I mean, a simple example. I have the point P at this, the coordinates are 3, 2, and I have the point Q, the coordinates are 5, 4. Again, these are coordinates of that point. Coordinates are different than the components of a vector. If I want to find U or the vector PQ, I do 5 minus 3, and that's the first component or the X component, and then 4 minus 2, that's going to give you the Y component. So what we get is just 2 and 2. And if I draw that vector, I start from 0. I go 2 and 2. And this is my vector U, which is going to start from the origin. Basically, when you find the components, it takes that vector and brings it to the origin. But the magnitude or the norm of the vector is the same. And I'll show you how you can find the norm of the vector in the next lectures. Now, I also wanted to do some vector addition and scalar multiplication example with the components. Let's say we have a vector U and these are the components 3, 4, and vector V 5 with components 5 and 2. If I do U plus V, let's see what we get. U plus V is going to give me 8 and 6. 8 and 6, that means the X component. First of all, this is vector U, and that's vector V. The components are 3 and 4, and basically you can see here and here it's 5 and 2, so it's 5, and you go up 2. So that's vector V, that's vector U. When you add them, you get 8 and 6. 8 and 6, this is 8, and that's 6. So if I draw that vector, you clearly see that is the diagonal of this parallelogram. If we do U minus V, it's 5 minus 3 is negative 2 and 2, and negative 2 and 2 is going to give me this vector. Negative 2 and 2, this is U minus V. But if I take the same and put it right here, you see how we form the triangle. And again, I can say this is U, U minus V. Now, let's talk about vector spaces. Vector space definition, let V be a set on which two operations, the two operations, main operation is vector addition, and again, if I put a plus sign with a circle, I mean vector addition, and if I put a dot inside a circle, that means scalar multiplication are defined. V is a vector space if the 10 following axioms of abstract vector spaces are satisfied. So each time you get the question, is this a vector space, you have to check all these 10 axioms. So the first 5 is about vector addition, and the second 5 is about scalar multiplication, or we can say that. So the first one, you check U plus V, or no, this is just this is scalar multiplication. So I have all 10 of them. It's kind of mixed up, but in the next video, I'm going to show you an example where the 5 and 5 are organized. So when you add the two vectors, they have to be in V also. We call that closure under vector addition. When you do R times V, and R is not a vector here, so this is also in V. So this is called closure under scalar multiplication. U plus V should be equal to V plus W. That's the commutative property. U plus V plus W should be equal to U plus V plus W inside the parentheses. So it's just the associative property. Existence of zero vector. Zero is in V, and that's how you show a zero vector. So by putting an arrow on top of zero. So such that the zero vector plus a vector in V, or V plus the zero vector in V is just that vector. So that's the zero vector, or you can say the additive identity. And of course, the existence of additive inverse, V plus negative V is going to give you the zero vector, or negative V plus V is going to give you also the zero vector. Then you have the distributive property of ordinary addition over the scalar multiplication. R pluses, these are scalars, times V should be R times V plus S times V. The distributive property of vector addition over scalar multiplication, R times U plus V, you can distribute the R actually. So you get R times V, U plus R times V. The associative property of scalar addition, R times S times V is RS times V, or you can write that as S times R times V. Again, this is simple multiplication of numbers here, but that's the scalar multiplication to a vector. And finally, the multiplicative identity, and 1 times V is going to just give you V. So that's the 10 axioms. In the next video, I have done an example which you can check, and you can see how you can check all these 10 identities and then see if it's a vector space and not a vector space. Once you understand the vector spaces, then we will talk about the subspaces. I think that's it. Please watch this video a couple of times, 2 or 3 times. Not many examples about vector spaces, and that's going to be the next video, but know the operations of vectors. How you when you add two vectors, what happens when you subtract them, what happens, and when you multiply by a scalar, what happens. And I think that's it. Thank you for watching, and I'll see you in my next video. Have a good one, everyone.